Good afternoon, everyone. This is Adam Green from ATA Engineering, and welcome to this webinar on optimization of hypersonic engines using STAR-CCM Plus and HEEDS. Basically, if you have questions during the event, if you could put them in the chat. Everybody is muted. We can unmute people at the end if they have verbal questions, but if you put them in the chat, we can answer them for everybody to hear. So with that, I will get started. I'm Adam Green from ATA Engineering, Account Manager. I'm joined by Chris Stoich from ATA Engineering also to talk in more detail about STAR-CCM Plus and HEEDS relative to Scramjet engines. Now, a few notes about who ATA are. We're basically an engineering consulting company in the US. We're an employee-owned business, and basically we have around 190 full-time staff members, many of whom are PhDs, and really we're a very skilled bunch of folk. We work on hard problems, and obviously CFD with hypersonics and optimization counts as one of those. So what areas do we work in? We work primarily in aerospace and defense, but we do a lot of other industries, robotics and controls, industrial mining, and some consumer products. But more recently, themed entertainment has been an interesting one for us for structural and safety aspects of themed rides. We also have offices throughout the US and mostly in centers of aerospace excellence in the country. And we will focus on basically design, analysis, and test. And really, we use in depth nearly all of the Siemens SimCenter tools to do a lot of that design and analysis. And then we have an extensive test group that travels both in the US and internationally to do various real-time testing of structural equipment and so forth. So, and really in extreme loading environments as well. ATA is also an employee-owned business, which basically means that everyone owns a piece of the company, and that really benefits all our clients because we can all be more productive and responsive because everyone's working towards success. And so we really strive for customer delight, and it shows in the reviews we get from our clients. And on the software side, we are a platinum partner for Siemens. We have a full support team and hotline support. We also do NASTRAN and FEMAP training, and really basically are a very skilled bunch of folk in our teams for supporting pretty much all of the SimCenter portfolio, especially STAR-CCM Plus, NX, and FEMAP. So let's dive into a little bit about what we're going to talk about today. And really, we're going to talk about two primary products from Siemens in the SimCenter portfolio. One is STAR-CCM Plus, which is a CFD tool, and another is HEEDS for automation and optimization. So I'm guessing many people on this call are familiar with STAR, but let's talk a little bit about what makes it really good. It's really basically a multi-physics CFD platform, and really has made its mark in the industry by obviously being firstly very, very accurate in terms of physics, but also being very user-friendly and very efficient at doing automated processes. And so a complete model can be run within a single environment and then rerun very, very easily. And so, combined with the advanced physics, productivity for STAR has really accelerated the market as a whole. And so how does that kind of manifest itself from a usability point of view? And really, STAR starts off with native CAD, often NX, because that's the main Siemens CAD tool, geometry cleanup, robust unstructured meshing, and then advanced physics really make that flow very easy. And this flow is automated so that once you've done it once and you want to change some CAD, then doing it again is very quick and easy. And that lends itself to optimization and putting it within a HEEDS wrapper, which is what we're going to talk about today. So really using STAR to create automated workflows and then putting those into a full sweep of optimization is really the name of the exercise we're looking at today. So step one of that, obviously CAD is the first part, and geometry cleanup are the second, but really the advanced physics and the ability to tackle this, hypersonic flow is the next step in how to get results in this space. And so STAR is very good at that already, and really one of the reasons why it's so successful. Here's an example of the Delta rocket and booster separation. And this is interesting because obviously it's transient, it's shock waves, and it's adaptive meshing. And if you look at the graph on the right there, you can see that different methods were used during the simulation. To start with, AMR stands for Advanced Automated Mesh Refinement. So initially there's no mesh refinement, and then it becomes steady mesh refinement. And then as the bodies move and break away, it then becomes basically a DFBI transient overset problem, which really uses almost all of the meshing features within STAR-CCM+. If we run this animation, you can see what I mean by that. So this is an animation of these booster rockets falling away. In a moment, you'll see how the mesh changes as this simulation develops. So you can see at the bottom, no AMR to start with, then some mesh refinement as it progresses, and then overset meshing to actually account for the moving bodies against each other. And so with basically establishing that STAR is very good at this particular subject, then what is HEEDS? Well, HEEDS is multidisciplinary design analysis and optimization tool. It sounds like a mouthful, and it is, but basically it does a couple of things. One is that it automates workflows, and then it does design space exploration and optimization. And really coupling it with STAR gives it the best of both worlds, because that automated workflow that's really inherent in STAR really lends itself very easily to being driven by HEEDS. And that's partly why Siemens purchased Red Cedar those years ago. And so HEEDS is a tool that can link together various parts of the analysis workflow. It works pretty much with all of the SimCenter portfolio, and it also works with almost any analysis tool, from competitors. So ANSYS and CATIA and all of those other tools that people are often using, HEEDS can talk to. And that means that if you've got a diverse set of tools in your analysis workflow, HEEDS can bring them all together for a workflow pipeline. And that is one of its great powers, to be able to bring a simulation together in an automated way, even using different tools from different vendors. And what makes it useful? Basically, the three down the left are the key things. Obviously, ease of use. It's very easy. It's very drag and drop onto a screen to build your workflows. And once you've got it rolling, then accelerated designs are a byproduct of that. You can run many more simulations without a man in the loop, and to get better design much faster. Integration with HEEDS HEEDS with CAD and CA tools, it's really unsurpassed in the industry. And the benefits on the right, you can see more innovative solution, better information and decision making. And then really the HEEDS team is very good at responding and making sure that everyone gets the best from their tools. So it's a great tool to work with. And so that all sounds good, but what does it look like in practice? And here's a very basic example, which I appreciate is a ship in a hypersonic presentation, but this is such a good animation that it's worth showing. And this shows a hull form of where the ship on the left is basically probably an NX, but could be in Rhino. The weight of the ship based on changes in the geometry is calculated. STAR-CCM+ does a hydrostatics calculation with just the weight and the geometry to establish basically how it's going to float in the water. And then that is pushed into a full resistance calculation for a STAR-CCM+ model. And that can then all be done again, basically automatically with no man in the loop, to really evaluate different geometries and how basically resistance can be minimized while maintaining functionality. So we move on a little bit to a more relevant kind of example. This is a transonic airflow design, really basically to maintain lift in the airflow, in the wing, but minimize the drag. And so in this time, the geometry was controlled using these spline control points around the geometry. And you can see when we run it, this does a similar thing. It's looping around the geometry changes, it's running a STAR-CCM+ simulation, and then it's coming up with different or better designs. And along the bottom here, you can see that this is the progression of the results from HEEDS, and this is the tide line for which is the best design. The red ones are probably designs that didn't meet the lift criteria up here. And you can see basically HEEDS marches through its design tables and comes back with better designs. And it might be running 200 models. In fact, we can see it's running 250 models or 300 out of a full design space in the millions. And so that's part of the HEEDS strength, to really cut down the number of models that it has to run to still come to better answers. And the other thing about the HEEDS and STAR-CCM Plus connection is that once you get to that point where you've run this and you've got a better answer, then you can go back to the STAR models and really understanding from an engineering point of view what makes the improved design better. What are the reasons that's better? So you can go in and look at the baseline design. You can look at the improved design that's come out of this process and really understand why it's better, and really help you, basically educate you in terms of what's going on with this scenario. Now, last year, Chris and I did another webinar, basically looking at a thing called the Whitcomb rule. When in the 1950s, the US were trying to push jet aircraft past the sound barrier and were struggling because they kept putting bigger engines but couldn't actually get past the sound barrier. And so they basically spent years working on this thing called the geometry of the fuselage, and the Whitcomb rule came out of it, where over the wings the fuselage needed to be narrow. So it took them a long time physical modeling back then, and we thought it would be fun to see if HEEDS could get that same answer overnight. So this was a test case, and you can see where HEEDS could modify the geometry at different stations along the fuselage. And HEEDS was able to find basically the answer overnight after 150 designs. And so this is how it looked when it was running. It's basically looking at reducing drag and modifying the geometry as we go. And so again, that's another example of the automation between the two tools, really letting you run much more simulation nodes and really helping you focus on a better design without a man in the loop. Again, all of these examples are with no man in the loop. They're obviously setting it up, but once it's run, once it's running, engineers can move on to other subjects. And so the last example here is really, it's not so much HEEDS, but it's more STAR coupled with workflow automation. And that is that if you've got aircraft or craft that are going to travel hypersonically in or out of space, obviously, a lot of the time you need to build databases for hypersonic flows, for lift and drag and things like that. And so STAR, with its automated tools, can actually help you do that. This is an example of an HL20 craft. And if you look on the right there, you can see it's a poly mesh, and the mesh is refining around the shockwave on the front of it at Mach 10. So using this, it's very quick to create tables of lift and drag for different angles of attack. And so you can see if we run this, basically looking at first the results versus experiment for the angle of attack versus lift, and the angle of attack versus drag. You can see obviously STAR does very well from a physics point of view at getting the results close to the experimental results. And then being able to automate that to create and populate these tables is very strong. So with that, I am going to pass the ball to Chris to start talking about how we used all of these tools in hypersonic engines.
I was muted at first. All right, Adam, can you hear me?
Yeah, you sound good. We can see your screen.
Great, thank you. Thank you very much. Yeah, as Adam mentioned, my name is Chris Ostojic. I'm a project engineer here at ATA and use both HEEDS and STAR-CCM on the majority of my projects that I work on. I'm also a dedicated support engineer, or DSE, for both those projects, providing software support for our software customers. So today I'm going to talk to you a little bit more about the technical aspects of how you use HEEDS and STAR-CCM Plus to improve the design of a scramjet engine in a hypersonic flow. So in this first chart, I'm showing kind of the applicability of different engines across various Mach numbers. Most of us here in this webinar have probably, traveled at low Mach numbers on commercial airlines or commercial airplanes that use turbojet engines. Above the applicability of those turbojet engines, you see vehicles that start using ramjet technology, in which there's not a compressor with moving parts, but instead a fixed geometry that creates shock waves to compress the flow down to a down to a subsonic speed in the combustor. However, above around Mach 5, there starts to appear some issues with the way ramjets work. There are large losses and increases in entropy as the flow passes through a normal shock on its way to subsonic. And then also just accelerating a highly hypersonic flow to subsonic speeds creates large temperatures, which present structural issues and also reduce the efficiency of combustion of your fuel in the combustor. So that leads to the idea of a supersonic combustion ramjet, or scramjet, which again uses a fixed geometry to compress the flow through a series of shock waves, but produces a supersonic flow in the combustor. And using this technology, as you can see on the right, you can move to very high Mach numbers while still producing higher specific impulse than just a rocket engine. Okay. All right, and so scramjet engines are complicated, they're integrated, and they're highly coupled. I'm just going to highlight a few different sections. Generally, there's an inlet, which may include kind of a four-body compression ramp. Anyway, this compresses the flow entering the engine. The flow then passes through an isolator, which further compresses it through a series of shocks, but also helps prevent inlet unstart due to pressure rises in the combustor and etc. In the combustor, energy is added to the flow through fuel addition, and supersonic combustion takes place, and then that flow is expanded through the nozzle, producing thrust. So in this webinar, we're just going to focus on the first two sections, essentially, the inlet geometry and then also the isolator geometry. And we have the objective of maximizing the amount of compression performed and then minimizing the losses generated during the compression process. Okay, and so I know that Adam already introduced STAR-CCM and HEEDS, but I'll just kind of reiterate what makes STAR-CCM good for hypersonic applications. It includes virtually all aspects of hypersonic flows. It includes turbulent aerothermal heating, fluid thermal structural interaction, radiation, combustion, and surface chemistry. These kind of three images show a few of those. On the left, we've got combustion simulation using a flamelet model. In the middle, this is a conjugate heat transfer problem. So we're looking at the temperature field within the structure. And then on the right, we've got a hypersonic vehicle doing what it does, traveling hypersonically. Then on the next slide, just an introduction to HEEDS. Again, Adam went through this. It's a multidisciplinary design, exploration, and optimization software package. I apologize that you already saw these videos in Adam's portion of the presentation. I didn't realize that he had stolen them from me. No, just kidding. But so here's another look at kind of how HEEDS kind of automates the search for a better and more robust solution within a design space, and dramatically reduces the time to both arrive at that design, but also reduces the amount of analyst time needed to find that design. Okay, and so on to our specific example here. In this webinar, we're looking at the design of a two-dimensional fixed geometry scramjet and its optimization. We have parameterized the two-dimensional scramjet shown on the upper right by 5 different parameters. What I'm calling isolator height, this cowl angle, and then 3 other heights that I've called H1, H4, and H6. Now, I want to stress that scramjet engines are very complex systems that shouldn't be boiled down to 2 objectives, but for the purpose of this demonstration, that's what I'm doing anyway. My objectives in this optimization study are to maximize the pressure increase by the time the flow gets to the combustors. That's just aft of H6 here, and then minimize the entropy increase or minimize the loss as the flow is being compressed. Again, taking the entropy at the combustor and comparing it with the entropy of the free stream flow. And so I went ahead and did this for just a single Mach number case at like a Mach 4 cruise condition. I ran 500 designs in a multi-objective optimization, and here you can see the results of this. This is the population of all of those designs and their performance as it relates to both the entropy increase and the pressure increase there. You can see that a number of designs were not better than the baseline design. And then during this process, HEEDS kind of tries to form this Pareto front or a non-dominated set. And this is the population of designs for which, if you took one of those designs and tried to improve on one of the 2 objectives, you would have to decrease the goodness on the other objective. So that's the Pareto front. You can see that not all designs on the Pareto front are good designs. I'm showing one on the upper right that certainly produces a large pressure increase, but it also has the negative aspect that it produces a fair amount of entropy increase. You can see that there's a pretty large normal shock at the inlet, which creates a lot of losses at the expense of producing a large pressure increase. On the lower left, you can see kind of our baseline design, and then everything to the right and below that is a clear improvement over that baseline. It satisfies both of our objectives. And I'm highlighting those in green, and then kind of have just this blow up of that region there. And then just on the lower right, I'm showing one example of a good design. And you can see that the changes to the geometry of that good design over the baseline are subtle, but produce clearly better results. And then I'll just note this was a simple 2D CFD model. I was able to run all 500 design evaluations on 11 hours, or on my desktop computer over 11 hours on 2 cores. But you can be sure that both of these tools can be used on much larger, much more computationally expensive models. In the example that Adam had given for the transonic vehicle, we were trying to kind of find the Whitcomb area rule. We were running those, that was a full 3D simulation, and we were running those in parallel. In fact, sending those jobs, or we had HEEDS sending those jobs from our local desktop to a rescale cluster in the cloud, and then pulling down the results. So it's this is very scalable. Okay, so getting back to our example, it happens that design 485 gave the best combination of pressure and entropy increases for this Mach 4 cruise condition. However, an engine needs to perform across a range of Mach numbers. You can't just it can't just suddenly appear at Mach 4. It has to accelerate up to that. And in fact, the lower a scramjet engine, the lower Mach number a scramjet engine can operate, the better, because it reduces the requirements of you know the lower Mach number propulsion system that you will need to have in your vehicle. But what this did do was give a distribution of parameters for designs that performed better than baseline. I may or may not have, when I set this up, not really known what I was doing, and I picked a large parameter space, and I saw that that produced some bad designs. So I can take this kind of reduced parameter space that I'm showing in the upper right, and you know, narrow my the space that I'd like to explore. And so HEEDS allows you to optimize over a collection of load cases for a single design. Odds are, when you're designing something, you know, be that a hypersonic, you know, scramjet engine, or some sort of structure where you need to minimize weight but still maintain a certain amount of strength, it's going to be subject to a number of load cases. So you can't just optimize for one of those. HEEDS allows you to, for each given design, loop over a number of load cases. So in this case, I've got a little screenshot of what a HEEDS study looks like on the right middle of the screen. And you see there's two analyses. The first analysis is a STAR-CCM simulation. And then around it is this little, like, kind of blue lasso, and that's our loop. And I've told HEEDS, hey, for each design, I'd like you to loop over 7 Mach numbers between 3 and 6. After it runs all of those simulations at each of those 7 Mach numbers for a given design, it then passes those results to a Python analysis to the right of it. And I just tell Python, hey, can you sum these up for me? And spit out the sum of the pressure increases and the sum of the entropy increases for you know, a given design. And those are my new objectives, as shown in the yellow box here. Of course, Python can do a lot more than this, but it was just a convenient way for me to understand the performance across a range of Mach numbers. So I set this up and ran a 200 design optimization. And here are the results. Again, this shows all 200 of those designs, which took 43 hours in this case, on 6 cores, again, on my desktop computer. I'm running 200 designs, but at 7 Mach numbers each, so that's 1,400 simulations. Again, we get a Pareto front that kind of looks like the previous one, and some of those are not necessarily good, as I'll show in the next slide. But there is, again, a population of designs that are clear improvements over the baseline. So in this slide, I'm just showing a few examples of what some of the designs look like. On the left, I've got our baseline design, and I'm showing it at Mach 3, 4.5, and 6. And it's got an average pressure increase over all the Mach numbers that I simulated of 196. And then an average entropy increase of 30%. To the right of it is an example of a bad design, which has a very high average pressure increase of 849%, but also carries with it a penalty in terms of entropy increase of 55%. And you can see that it, in fact, unstarts at Mach 3, pushing that shock outside of the inlet. So that's definitely not what you want. And then to contrast with that, we've got a good design on the right here. It's got an average pressure increase much higher than the baseline design of 535%, and then also an entropy increase that's lower than the baseline design at 28%. And you can kind of see, if you contrast the good design versus the baseline design geometry, you can see where some of the differences exist. The corner between the compression ramp and the isolator is kind of smoothed out a little bit, and then it's also got some slight area variations as you move downstream in the isolator. So HEEDS does more than just suggest specific designs that a designer should use on their final product. It also provides a suite of post-processing tools that allow further insight, which is necessary. There's probably some additional design constraints or manufacturing constraints that a designer has to take into account that aren't implicit in the computational models. So HEEDS allows you to use, again, powerful post-processing tools to gain insight as to what makes a particular family of designs good. So here is an example of one of those post-processing tools. Definitely not the most powerful, but I think relatively clear. And this is a correlation table. So I'm just looking at the population of good designs and how different parameters correlate with each other and the objectives. So it's kind of an eye chart, so I'll walk you through an example. Whoops, look at pressure increase. So pressure increase has a strongly negative correlation with this height H6. That means that a decrease in H6 leads to an increase in pressure, and this makes sense. It's a hypersonic flow, and so a decrease in the area in the isolator will lead to an increase in pressure. However, if we look at entropy increase, we find that a decrease in H6 also leads to a decrease in entropy. So clearly, decreasing H6 kind of is something that we might like to do to increase the performance of our engine. Another example, if someone's interested in mass flow rate, you can see that increasing the cowl angle will decrease mass flow rate. And those are just a few examples of some of the insights you can gain from this post-processing tool. So here I'm showing a video which is kind of scanning through all of the population of better designs that I found. You can see that they don't all look the same, and some may perform better or worse at different Mach numbers. So really, the designer might want to use one that performs best at the cruise condition where they plan to spend most of their time. And so, yeah, HEEDS has given us a number of different designs which behave differently. And here are just 4 examples. We've got design 104, which I have colored blue, and this particular design produces high compressor pressures at low Mach numbers. In contrast, design 197 produces high combustor pressures at high Mach numbers over here. And then design 111 gives kind of a flat performance across the entire Mach range, and then design 161 unstarts, and you can see this, so that's garbage. We don't want that. But you can see that the kind of jog in the mass the mass flow at the lower Mach numbers, indicating that that inlet shock was pushed out of the inlet, and now we're spilling flow around the engine inlet. Okay, and so I'm going to wrap up here. STAR-CCM Plus and HEEDS clearly provide a significant advantage to scramjet engine designers. STAR-CCM provides accurate predictions in the hypersonic regime with its high-performance discretization schemes and high-fidelity physics models, while HEEDS intelligently explores design space to automatically simulate viable candidate designs and produce performance predictions for hundreds of design variants. And again, this is without analyst intervention other than setting things up and pushing go. I also want to note, I didn't say this earlier, but one thing that I really enjoy about HEEDS is if, for whatever reason, it could be numerical or it could be a hardware issue. If a design fails, or sorry, a simulation diverges, or something happens, that doesn't ruin the whole study. HEEDS just notes that, says, hey, for some reason this failed, I'm moving to the next one. So you're not going to push go at the end of your Friday and then come back on Monday to find that something failed later on Friday and you waste the entire weekend. So with this all-star team of STAR-CCM Plus and HEEDS, this allows you to explore not one but hundreds of designs, and you can make important design decisions within closer to hours and not weeks, of course, depending on the size of your problem. Anyway, this allows you to accelerate your design process so you can discover better designs faster. And that's my final slide. So Adam, did you want me to pass it back over to you, or?
And that was great. Thank you, Chris. Well, I think we could maybe stay on your screen because we have a couple of questions in the chat. Peter asked about basically extending this to maybe 3D or adding combustion. Can you comment on if that's feasible?
Yeah, of course it is. STAR has an embarrassing amount of physics models to kind of address any issues that any level of complexity that you'd like to solve, and extending to 3D is very easy to do, and in fact gives you in the current release, it gives you access to even more kind of useful meshing tools such as adaptive mesh refinement and such. So yeah, of course you're gonna have to spend a little bit more time computing the answer, but otherwise it's simple.
Chris, maybe I can add to that too, and that is that when you're doing a HEEDS automated workflow and you're looking at automated processes where you probably want to run at least say 100 points, maybe 200 points as a reasonable expectation, then you've got to get your simulation time down per point to be realistic. Obviously, if you've got let's say we're going to run 100 points, you can't run a CFD model that's going to take a day to run 1 point, and that's kind of really where the challenge is with CFD in this mode, that you want to keep the model size down where it can run in a realistic time and not take 3 months to give you an answer. And there's a couple of ways to do that. One is to simplify the model so that it can run quickly, and that's what we've done here. The other is to put it on the cloud and run it on 1,000 or 5,000 cores, and STAR can do that too, and within the realms of can the model scale and give you an answer quickly. So that's part of the challenge, to make sure that in order to run 100 points, you can do it in a time that's acceptable to everybody. So I think that was the main question in the chat. If anyone's got any more questions, please let us know now. Otherwise, we thank you for your time. And this webinar will be, it has been recorded and will be up on our YouTube channel and on our website. So everyone who's registered will get basically a link to that and can access it later. We just have another question come in from Ashwin Babu, and he says, let me read it again. Sorry, actually it disappeared. can HEEDS support exploration over coupled models like, say, FSI pressures on a body due to fluid flow over it? I'll let you take that, Chris, but I think the answer is yes.
Yes, in a number of ways. So within STAR-CCM Plus, it's a multi-physics solver, so it can solve fluid structure thermal interaction problems, and those capabilities are being improved with each release. So you can throw one of those models, just one of these FTSI models that are in STAR into HEEDS and perform the optimization study. You can also integrate some other structural tools that you might be using, such as NASTRAN or FEMAP or whatever, and put that in the loop in HEEDS, and HEEDS can manage kind of the handshake between STAR and whatever other physics solver you'd like to include.
And Chris, maybe I can add to that too. And when you're talking about coupled models, obviously you can run STAR and you can connect it to a structural code and run them together, and HEEDS can drive that. But HEEDS can also create a loop where the two are run independently, and maybe you're running a flow model where you then want to assess the forces on a body. Those forces are exported, and the FE model is run separately, so that you can tackle a flow problem where you want to optimize flow, but you also want to make sure that the design that maybe is the best flow is also strong enough. Those can be separate items on the HEEDS workflow. They don't necessarily need to be co-simulation, but they still could be in the HEEDS workflow. So it is one of the powers of HEEDS where you can really drive these automated flows, even to the extent where part of the HEEDS model could be the cost of the metal in a magnet in an engine, and hence I want to make sure that the device performs. I want to make sure it's strong enough, and I want to make sure it's as cheap as it can be. So all of those can be targets in HEEDS and really make it very powerful. I think we have another question here from Clement, and he says, why not start the Mach number range lower, since the transition model is typically lower than Mach 3? Can you take that, Chris?
Yeah, for sure. That's a good question. It was just a choice that I made in preparing the seminar kind of material. It definitely would be interesting to try and decrease that Mach number as much as possible, and it would have been potentially a slightly more interesting example if I had done that. So sorry for the disappointment there, but
all right. Well, thanks a lot, everyone. We appreciate your attendance this afternoon, and please look for that email with the links to where you can view this or share it with your colleagues. And we thank you for joining us this afternoon.